Hello everyone, my name is Keerthi. Today I am here at DVCon US 2020 and today I am here at OneSpin's booth. And today I want to show you all about or talk to you about how to verify error correction codes using formal verification tools. And before I start, I want to say a few words about the title, why we kept such a title, the first part of it, which says formal verification by the book. The reason is simple, and sometimes when we start to verify some design blocks using formal, it's possible that the formal tools they run into complexity issues, and maybe the design is big, maybe the problem the tool is trying to solve is big or complex, but if we use the right approach, maybe there is a way to still formally verify these design blocks. And so we kept this title to indicate that with the right approach, the formal verification can really help us to exhaustively verify our designs. So that's the main intention behind this title. So let's begin this presentation. Okay, so what I'm going to talk about today is first I will introduce what are error correction codes and how they are designed. And afterwards, I will show three different approaches, formal approaches we used to verify these error correction codes. And to be specific, the first two approaches, so these are the state-of-the-art approaches for verifying error correction codes at the moment. And the proposed approach of this presentation is called linearity. And here with this approach, we exploit a specific characteristic of the ECC designs. And that's why we call this as linearity. It will be more, I will explain more about linearity, why we call it linearity and more on so. And I will conclude this presentation by showing some results of this approach and with a brief summary. Okay, so let's begin. So error correction codes, they're basically used in safety critical designs, mainly to safeguard memories against soft errors. So these soft errors may be radiation errors, may be caused by electrical glitches or magnetic interferences or etc. And so here the error correction codes, they basically work in two stages, and the first stage is called ECC encoding. And what happens during ECC encoding is, so for the input data, so here the input data is 256 bits wide. The input data is passed through an ECC encoder, and this ECC encoder computes the additional redundant bits. And the number of bits, so here the number of additional bits are 22, and they are selected based on different criteria. For example, one, it depends on the number of errors that need to be detected. Two, it depends on the number of errors that need to be corrected, and it also depends on the type of algorithm, the encoding algorithm we are using, and it may also depend on the bit error rate that we want to have in our design. And what happens here is, so for the input data, we compute the additional ECC bits, and then afterwards, the data, the original data bits together with the ECC bits are returned to a memory location. So without the ECC, we would have written only the data n bits. So now with the ECC, we add additional redundant bits, and these bits are going to help us to detect if there are any bit flips or bit errors. So it may happen during the lifetime of this device that some of the bits may be corrupted. So as I said before, maybe a photon or a radiation falls on the chip, and maybe a bit which is carrying a value of 0 may be flipped, and then now it carries a value of 1, and that means the data is not valid anymore. And this corrupted data, we call them as non-code words, because they no longer follow any code rules. It's not a code word anymore. And the next step, when this particular value is read, this read value is passed to the ECC decoder. And the function of this ECC decoder is to check which bits have flipped, that means to check where are the bit errors, and then set the corresponding flags. And in case if the number of bit errors are within the correctable range, correct the data. So these are the two operations performed by the ECC decoder. And here this ECC circuit, what I am showing here, this has the capability to correct up to 2-bit errors and detect up to 3-bit errors. So as you can see, there is a flag to detect single bit, double bit and 3-bit errors. So this is basically the overall picture of how ECCs work. So now we have seen the basic introduction to the ECC. So now let's see how we can formally verify them. So before introducing these approaches, let's first look at the setup, how we formally set up the environment. So here we have an ECC encoder and we have an ECC decoder, and in between we have the program flash interface. But for functionally verifying the ECCs, the interfacing with the program flash is not really needed. And moreover, the program flash will add unnecessary complexity for the formal proof. So that's why we do not want to have the program flash in our formal environment. So what we do, we implemented an RTL wrapper in which we instantiated only the ECC encoder and ECC decoder. Now you see that the write data that is coming out of the ECC encoder becomes the primary output of this wrapper, and the read data which is going into the ECC decoder becomes the primary input of the wrapper. And by assuming bit errors between the output and input, we can enumerate or we can imitate all the bit flips. So this is how we set up our formal environment. So now let's first see how did we perform the formal verification with the brute force approach. So here we call this approach as brute force because we are not implementing any optimizations. We are just giving the problem to the formal tool and asking the formal tool to solve the problem. And here what I am showing here is an SVA property to detect all 3-bit errors, triple bit error detect. And so this property is written in an SVA syntax, and what this property is saying is, so count once, $count once is an SVA system task which takes an argument and returns the number of positions which have a value of 1. So here this property is saying that assume that between write data and read data there are 3-bit positions which are flipped, and in this scenario prove that these flags have certain values. And in particular, because this is a triple bit error detect property, the triple bit error flag should be asserted. Similarly, the error detect out flag should be asserted because there is an error in the read data. But the single bit error and double bit error flags, they shouldn't be asserted. So this is what I am stating in this property. And when I run this property in a formal tool, so what is the analysis space? So what could be the complexity for the formal tool? Because there is no assumption on the data n, and the data n is a 256-bit vector, the formal tool can try to prove this property for every combination of this data. So now, because there are 256 bits, the number of input combinations is 2 to the power 256, which as you can imagine is a very, very big number. In addition, we say that there is 3-bit errors between the write data and the read data. So that gives us these many number of error combinations, that is all 3-bit error combinations in a vector of 278 bits. So these are multiplied and the resulting number is the analysis space that the formal tool has to check. And this is a very, very big number, and practically speaking this is not a reasonable complexity for a formal tool to solve. So what happened was, when we tried to prove this property in a formal tool, We ran this property for around 5 days, and even after 5 days, because there is a limitation on the memory and the time, so the tool ran out of computation resources. And so the tool, after 100 hours of computation, it ran out of time. So with this approach, with the brute force approach, we were not able to get any conclusive proof on our properties. So that's why we started to make some optimizations, and the first optimization we did, and we call it as divide and conquer. And what is the basis of this optimization? So we realized that the main problem was a huge analysis space. So we thought, so let's try to reduce this analysis space, and let's see if the formal tool can solve this problem now. So how did we do it? So in the divide and conquer method, so we have a data vector of 256 bits and 22 ECC bits. So what we did was, we wrote a property which states that, so the first 240 bits of the data vector, which is denoted in the first line of the property, is constrained to a constant value. In addition, the ECC bits together with the first 240 bits of the data vector are assumed to be error free. So here, that is what is denoted in the second line of this property, which says that the write data of these bits is equal to the read data of the specific bits. So that means the formal tool now has no room to play with these bits, so it has to be fixed to a certain value. But now we say that the 3-bit errors can occur only in this small window of 16 bits. So that's how we are reducing the analysis space. And the proof part, the commitment part of the property, remains the same. And now if we analyze the analysis space here, because now the formal tool can only play with 16 bits, the number of input combinations are 2 to the power 16. And because we say that there is no error in the rest of the bits, the bit error should be assumed only within this range. And because of this, the analysis space is quite manageable, and this is a fairly manageable number for a formal tool. But here it will not be enough just to have one property, because we have to repeat the property for the entire bit vector. So in this case, we will have around 16 to 17 properties for 3-bit detect properties. So in this method, because the analysis space is manageable, we were able to get the full proof. That means we were able to get a convergence on the property. But there are some drawbacks of this approach. The first drawback is that we have a large number of properties, and the main issue here is the coverage issue. So what is the coverage issue? So the specification for an ECC design states that all 3-bit errors or 2-bit errors or single-bit errors should be detected and corrected. But here, what means all? So all means 1-bit error can occur in the most significant bit, and the other bit error can occur in the least significant bit, and another bit can occur somewhere else, right? But in this problem formulation, we are not verifying such a scenario. So that means we are not completely verifying what the specification states. So that's why with this approach, we have a verification gap. So we had to do some additional simulation to back up this approach. So again, this approach didn't give us the results we were looking for, because there was a coverage hole. We started to do more experiments, and we call this approach as linearity. And why we call this approach as linearity? Let's see. So, so this is the ECC formal verification setup, what we have. We started to look more into the RTL part. So what exactly the RTL is doing here? And we started to look more closely into the RTL, and what we found out was that there is a very important component within ECC decoder which is doing bulk operation of the ECCs. So this is a simplified block diagram of the ECC decoder, and as you can see, there are basically 3 important components. The first one is syndrome generator, and the other ones are error detection and error correction units. So what does the syndrome generator do? So the syndrome generator takes the red data, and for this data it generates a syndrome. Based on this syndrome output, the error detection and correction unit, they perform their corresponding tasks. So but here the main component is the syndrome generator. And so we started to look more detail, we started to perform some additional experiments on syndrome generator. What is its behavior? We found out that when the write data is same as the read data, which means that there are no bit errors. In such a scenario, the output of the syndrome generator is a null vector, is always 0. Regardless of the value in the write data, whenever the read data is equal to the write data, the output of the syndrome generator is always 0. So this is the first finding. And then we started to make few more experiments. What we did was, we tied the data in to a constant value, and then we inserted a bit error at the 5th bit position. Then we looked what is the value of the syndrome generator. We found out that the value of the syndrome generator is phi, which indicates that the bit flip occurred at the 5th bit position. Then we took a different data value, different data in value, but again we inserted the error at the same 5th bit position. Now the output is again the same, again telling us that the bit flip occurred at the 5th bit position. We did more such experiments, and here we inserted the error at the 16 bit position, and the output indicated that the bit flip occurred at the 16 bit position. So with more such experiments, we were able to realize two very important conclusions. And what are those? The second one is that the output of the syndrome generator is independent of the data in value. So this is a crucial finding of these experiments. And the second finding was that the syndrome output, it doesn't depend on the data in, but it depends only on the erroneous bit position. So now, so these findings are crucial for this approach, but the question remains, why the output of the syndrome generator is independent of the data in? So what quality or what characteristic of syndrome generator that makes it independent of the data in? The reason is the syndrome generator is implementing a function which is a linear function. So now what is a linear function? If you recall the linear algebra, a function f is linear if it follows this rule. What is this rule? If f of x, sorry, a function f is a linear function if f of x plus f of y is equal to f of x plus y. So here it simply says that regardless of the input arguments x and y, this function preserves the addition operation. So that's what the linearity here is. And how can we compare it to the syndrome generator? So let's assume that sin x is a function implemented by this syndrome generator. So where x is an arbitrary data vector, so here it's a read data. The syndrome generator takes the read data and then it computes the syndrome. And we denote this function as sin x here. So sin of x XOR y is equal to sin of x XOR sin of y. And so we know that the XOR operation performs the bitwise addition. So we can say that syndrome of x plus y is equal to syndrome of x plus syndrome of y, which is nothing but the syndrome generator is implementing a linear function. So this is the reason why the syndrome generator, the output of the syndrome generator is independent of the data in, because it is preserving the bitwise addition. And now, since we know that the syndrome generator is implementing a linear function, and also what is the output of the syndrome generator when there are no bit flips, we can capture them as properties. So here the first property says what should happen when there are no bit flips. So when write data is equal to the read data, the output of the syndrome generator is a null vector, and we capture it as a property. And the next property, we are trying to prove the linearity. So syndrome of x XOR, again XOR is performing the bitwise addition. Syndrome of x plus syndrome of y is equal to syndrome of x plus y. So once we prove these properties, it is proven that the syndrome generator, the output of the syndrome generator, is independent of the data n. And once we prove this, we still need to prove that the detection and correction is working properly, for which we still need the original properties. But here we don't need to verify these original properties for the entire input combinations, because we already proved that the syndrome output is independent of the data. So what can we do? We can assume an arbitrary chosen data word, and then we try to prove the rest of the properties. So this is a new property which says, here I assume that the data in, I fix this to a constant value, and then I assume that there is a 3-bit error between the write data and the read data, and then the commitment part of the property remains the same. Now as you can see, because the data input is fixed to a certain value, the tool cannot play with this input anymore. Now what is the analysis space? The analysis space is 1 multiplied by all 3-bit error combination in a vector of 278 bits. And compared to what we had before, which was 2 to the power 256 multiplied by this value, is basically 1 multiplied by this value now. So there is a significant reduction of the analysis space, and as a result, when we run this property in our formal tool, the property converges within 2 hours. To be specific, the property converges in 1 hour 45 minutes. And this is the approach, and so what I showed so far is just one property, but we need such properties for detecting 2-bit errors, detecting single-bit errors, and corresponding properties for determining the correction capability of the circuit. So now let's see what are the results on some of the designs we ran this approach on. So these are the designs where we use this approach, and the first design is a big SoC. It had 2 instances of ECC circuits. The first instance was inside the program flash, and the second instance was inside the data flash. And so the second column shows the number of data bits and the corresponding ECC bits and the detection and correction capabilities of the circuits. So yes, and for all our formal runs, for proving the formal properties, we use the tool OneSpin 360dB. And in case of our first approach, which I talked about before, which we call as brute force, because here the first 2 are quite big ECC designs with lots of huge input combinations. The formal provers, they were running out of resources, memory and time, and even after running for 100 hours, we didn't have any conclusive proof. But in case of smaller ECC designs, the provers are good enough to give us the results within few minutes. And in case of the second approach, which is divide and conquer, we had lots of properties. Although we had a coverage hole there, we were able to manage the complete proof. That means the conclusive pass on the properties. So overall, on the program flash ECC, it took 40 hours to prove all the properties. And in case of data flash, it took around 25 hours. And following the linearity approach, which is the proposed approach of this presentation, we were able to get the conclusive proof on all our properties on the complete property suite within 9 hours of property runtime. And this is for the ECC instance in the program flash. And in case of ECC implemented in the data flash interface, we were able to get the complete proof for all our properties within 7 hours. And as you can see, even for these small ECC designs, there is a considerable property runtime improvement when we run these properties with additional constraint on the data n. So these are the results what we obtained, and what is the takeaway, what is the conclusion of this talk. So if you have very big ECC designs, first try to prove the characteristics of the linearity property of the syndrome generator, and afterwards you can prove rest of the properties by assuming an arbitrarily chosen fixed data vector. And by following this approach, even for those properties which were which were not able to conclude with a conclusive proof, we were able to get a proof within 2 hours of runtime or less. And I would like to conclude this presentation with the following summary, that the linearity approach proposed in this presentation, we were able to significantly reduce the analysis space, because of which we were also able to reduce the property runtime. And as I said before, the properties that were given up previously now converge within 2 hours of runtime. And because now we don't have to develop complex properties, the properties basically become simpler now, and we generated all the properties within an in-house automation tool. And overall, including the automation tool and with the following the linearity approach, we were able to obtain a productivity gain of 10x to 15x. And again, I want to stress this point that whenever we do formal verification, so with some clever thinking, with some clever formulation of the problem, we can really benefit from the formal verification. Thank you.